So at the very beginning of the talk, Andy talked about advanced quantitative methods and not necessarily being difficult quantitative methods. And that's pretty much exactly true for matching. I'm going to sell you matching as a very simple method for causal inference, so much simpler than normal regression analysis. So what is matching in a nutshell? Basically, matching is when we try to create two or more groups of people that are vaguely similar each to each other so that we can later compare them for causal analysis. And it's a very important tool for causal inference in the social sciences, and it's been around for yonks, way before linear regression became popular. But it sort of fell out of fashion sort of in the sort of 80s, 90s, but had a massive resurgence in the 2000s. So you find matching all over the place when you look at health research, epidemiology, economics, and political science. But in some fields of social science, it's not really actually taught at all. So it might be completely new, despite the fact that it's not particularly horribly advanced. And it's a method that you can basically combine with other statistical methods such as regression modeling to give you huge advantages for effectively very little effort at all. And it's really easy to understand. But mainly the reason why you would want to use matching is for causal inference, which sort of leads me on to explain what is causality, really, which is a big question, but basically what the aspect of causality we're interested in is what is the effects of doing something X on Y. So does increasing immigration cause unemployment? Does social media cause more extreme sentiments? Does more education lead to better pay, cause better pay? So colloquially, you can understand that, but that's not a formal definition. So we're going to give you I'm going to give you a more formal definition of causality as a thought experiment. So imagine in a parallel universe where everyone had less education. So I didn't get a degree, I had far less education. Andy didn't get a degree, he had far less education. In this parallel universe where everything is exactly the same except for that, would our wages be any different? And if our wages were different, then that difference is the causal effect of education on wages. So keeping with this thought experiment theme, ideally, we would have some sort of magical dimensional machine in which we can see basically parallel world and look at people with degrees and without degrees and look at basically their wages in these parallel worlds. So let's take the people in red, Fry and Bender, on this table, and let's look at their wages, you know, in parallel universes where they had degrees and didn't have degrees. So basically, we just subtract the number in column 1 where there's wages if they had a degree versus column 2 where they don't have a degree, and we get the average treatment effect of 3.73. So basically, the causal effect of a degree for these two people on average is going to be 3.73, I don't know, virtual galactic dollars or whatever higher, which is great. That works out really simple. It's a simple table with a simple sort of mathematical premise. Problem is, of course, real life gets in the way, and it turns out that you can't sort of, you know, jump to alternate realities and sort of look at what people's wages are like there. So but we can still estimate that causal effect from the previous slide under circumstances in our reality. One of those circumstances is if there's just random. So basically, you get your treatment group, people with degrees, and if allocation to the treatment, i.e. whether people got degrees or not, was completely at random, then you can get a control group of people without degrees and just simply compare the average difference in wages between the two groups to get the exact same causal effect, which in this case, it's like 3.8784, which is very similar to 3.7 or so that we got in the previous slides. But that's basically under the ideal situation where basically allocation to a treatment is completely random. Of course, people don't get degrees at random. You usually have some sort of non-random selection. For instance, people that get degrees are also more likely to be more motivated, perhaps, and because they have higher motivation, they probably would have earned higher wages even though they didn't have degrees anyway, because motivation has a causal effect on both the treatment and the outcome that you're trying to measure. So what you have in this case is the case of you have some sort of confounding variables. And one way to adjust for confounding variables is to do matching, where so long as you observe what these confounders are, you can do matching to adjust your control and treatment groups to be similar with respect to these confounders. So for example, the most classic old school way of matching was exact one-to-one matching. So for every person in your treatment group, you found the exact equivalent person to go in the control group. So for instance, if your treatment group, if the only confounders were gender and age, and your treatment group had a female 16-year-old in it, you would find a female 16-year-old who didn't receive the treatment and put them in the control group. You do that for the next person in your treatment group, which might be a male 26-year-old. So you find a male 26-year-old who didn't receive the treatment, put them in the control group. So on and so forth, like that, until you filled up your control group, and then you just simply compare the average outcome between these two groups. Bada bing, bada boom, you're done. The thing about exact one-to-one matching, though, is it's horribly laborious and data intensive, which is why very quickly it fell out of favor. Because when you have a situation with loads of confounders, you're not able to do exact matching in that sort of way. But one of the statistical technique that can control for lots of confounders at once is statistical models like regression models, which is why you sort of get the rise of regression models in the 1980s and 1990s, and that's basically the predominant method that people use nowadays. But at the same time, matching has evolved since then. We can sort of match on much more variables than we have before, using different techniques and algorithms. The simplest algorithm is just nearest neighbor matching. So for example, imagine our confounders for getting a degree was just simply maths and English scores. So we plot maths and English scores in this scatter plot, and we color our treatment group red, and we color our control group, people without degrees, basically, in blue. Basically, for nearest neighbor matching, we simply find someone, for every person in our treatment group, we find someone who had who didn't get a degree, who is the most similar maths and English scores, and then we just basically do this pairing up, and then just chuck out all those cases which do not match. So basically, we just Marie Kondo up our data set and chuck out what we don't need. Then you check the remaining data set is sufficiently balanced, so your treatment group and your control group now look vaguely exactly the same, and then you run whatever statistical test or models that you were going to do on this sample anyway. So if you wanted to do linear regression, go ahead. If you just want to do a t-test on this data, go nuts. If you wanted to do some sort of chi-square test, yeah, whatever you were going to do anyway. So that's basically essentially it. Matching is basically like a pre-processing step that you take before any other sort of statistical analysis. I mean, there's other ways of doing matching, but that's basically the way that I'm going to pitch at you today. So why do matching at all if you're just going to run these other statistical algorithms afterwards? Well, first of all, there's just very little additional effort. Okay, you're not going to be matching control and treatment groups by hand. There's software to do it for you. It includes all the pre-processing steps that you have to do anyway. So you have to check for outliers and remove them from your data set regardless. You have to look at descriptive statistics, whatever, just combine them into your matching step. The more statistically robust reason why you should do matching is once you have a good matches, you are less reliant on statistical models and their underlying assumptions for your estimates to be unbiased, which means that you can sometimes get things horribly wrong and still produce the right answers, so long as you do this pre-processing step first. And what I said about Marie Kondoing up your data set and just basically throwing away data, that might sound like to you that this horribly affects the accuracy of your estimates, which is absolutely, turns out, not true. As I'll show you on the next slide, sometimes it improves the power of your statistical tests. So here is an example from the simulated data set. So now we're plotting the relationship between maths, a confounder, math score, and people's wages. So on the left-hand side, you can see the full data. Maths and wages don't have a linear relationship. It's sort of a curvy linear relationship. It goes up. and then it sort of plateaus and starts going down. Once you have really high math scores, your wages start dipping down. We could try to account for the effects of math scores and wages by just fitting a standard linear regression model. But as you can see, because the model that we fit says that there's a linear relationship between wages and maths, which is a wrong relationship. If we actually fit this model, we're going to get the wrong estimate for the difference between non-degrees and non-degrees, what we're counting for maths. So we're going to find out that degree holders actually earn like minus 88 virtual pounds less than non-degree holders. And that's simply because we got the functional form of that model wrong, which you're probably looking at this simple plot going like, I'll never get it wrong in a situation like this. But in real life data, you have tons of variables, which allows for interaction terms and whatnot. You don't know what the true data generating mechanism is, so you're probably wrong to some extent. On the right-hand side, you can see what happens if we do matching first. So we match and throw out all the data that doesn't, from the control group, that just basically doesn't match. Run the exact same wrong model with the exact same wrong functional form once again, we get a difference of basically 0, which is the correct answer. And that's because there's very little model extrapolation going on once we throw out the unmatched cases. Also, I put down the standard error in each of the cases and you'll find that on the right-hand side, the standard error is smaller for the matched cases. Even though we've just thrown out all of this data, the estimate that we get is more accurate than if we didn't. I'll leave you to work out why that is. So basically, another reason why we should match at all is not to do with statistics. It's because you can calculate much more interesting quantities than just the average treatment effect for everyone. So you can calculate, I've been talking a lot about the average treatment effect on people on the treated, but you can also calculate the average treatment effect on people who are untreated. So, for example, what are the effects of degrees on those who do not normally get degrees, which is probably a much more interesting quantity for public policy, because you don't necessarily always want to know just how this program is doing for people who got treated. You want to know, well, is there any benefit to expanding this program, and how much benefit would we get? We expand this program to treat people who are not already treated. And you just simply don't get that if you just run a statistical model and away you go. Why not do matching? Well, when the assumptions of matching are violated. So if you have the presence of confounders that you do not observe, so basically if you know that, for instance, motivation affects as a confounding factor in getting degrees and wages, but you don't observe that, well, matching can't help you here, but neither can most statistical models or any other statistical technique that you're going to rely on, unless you change your research design to maybe use longitudinal data, exploit quasi-experiments or instrumental variables. Statistical analysis won't really help you, matching or not. If you have the presence of peer effects, so for instance, Bender getting a degree shouldn't affect Fry's wages, but if that does, you have a violation of basically the stable unit treatment variable assumption, which is a very unique type of basically it's a very niche type. It's something that does happen, but once again, you're going to have to use a more niche advanced statistical technique to account for that. And also, you don't really do matching if you have a lack of common support, in which case the two groups you're comparing, treatment controls, are just far too different from each other. They have absolutely no overlap in characteristics, in which case, once again, you can put that through a regression model and give you answers, but don't trust those answers. Generally, you do not. That's also a sign of something bad happening elsewhere as well. So basically, what will we cover on the course? Basically, I've just given you this really quick whirlwind whiz through matching. I expect some sort of base proficiency in R and how to do linear regression in R, and then I'll show you how to implement very popular matching algorithms in So for instance, we haven't talked about propensity score matching. I haven't talked about automated ways of matching, such as genetic matching or greedy matching. You don't have to match one-to-one. There will be a brief introduction to causal inference, including all sorts of questions and terms such as things like, what does exogenous mean? And what are confounders really? What variables should I control if I wanted to do causal inference? And hopefully, the course won't cover every little aspect of matching because it's basically like a Subway sandwich. There's so many options in terms of matching algorithms that you can use. But hopefully by the end of it, you should be able to do the most popular matching algorithms for your own research if you wanted to, or at the very least, understand papers that use matching and all these jargon terms that they tend to use in them. And that is the end of my